The final piece of our discussion about distribution system storage will focus on O&M practices relative to storage and storage facilities. We'll start by looking at the impacts that storage can have on water quality. If you recall from our discussions about water quality way back at the beginning of the semester, one of the things that drives the degradation of water quality in a distribution system is water age. While storage facilities are prone to increasing water age, and you can have declining chlorine residuals, you can have nitrite problems as a result. So it's important that we operate the reservoirs in a manner that accommodates or at least mitigates some of those water quality issues. Start with the concept of turnover. Turnover is simply the idea of replacing the water in the reservoir on a regular basis, turning it over, so to speak. So if you have a 2 million gallon reservoir that you're flowing at, let's say 500,000 gallons a day through the reservoir, it would theoretically take 4 days to turn the water over. And that's the kind of math we talk about when we're talking about turnover. The recommended rate for turning over water in a reservoir in order to avoid degrading water quality is 3 to 5 days. So every 3 to 5 days you would want to refresh the water in the reservoir. Now, of course, one of the things that we talked about when we were discussing storage components is the inlet-outlet piping configuration, because if you've got a single inlet-outlet pipe, you can do all the math you like to suggest that your turnover is happening in 3 to 5 days or 2 days or 10 days, but if it's constantly replacing only the water around that inlet-outlet pipe, then you're going to have water that is fresh around that pipe, but at the perimeter or maybe at the upper levels elevations of the water within the reservoir, you could have significantly older water. And the concept of water within a reservoir that is of different levels of quality at different parts of the reservoir is called stratification. As you can see in the exhibit, you've got a common inlet-outlet pipe, so the water at the bottom of the reservoir, relatively close to that inlet-outlet pipe, is relatively fresh. And as you get to the upper elevations in this particular example, you get a level of stratification and different levels of water quality to a point up at the top where it is water that has not really moved for potentially a great period of time. That can also happen at the perimeter of a very large reservoir. If you've got a reservoir that's got a diameter, let's say even of 150 feet, which is pretty common for a 2 or 3 million gallon steel tank, and you've got a common inlet-outlet pipe, not only do you have water at the vertical stratification, but you've got water that is around the perimeters of the reservoir or on the opposite side of the reservoir from where the inlet-outlet pipe penetrates the wall of the reservoir, that is also not moving. And the older the water gets, the bigger of a problem you're going to have. In addition to the stratification associated simply with the lack of mixing or circulation of the water, you can also have thermal stratification. Thermal stratification is the layering and the separation of water based on different water temperatures. This in and of itself can also lead to higher water ages, which result in loss of chlorine residuals, increased nitrites, potential taste and odor complaints from customers. Essentially what happens is water that enters the tank during a fill cycle is typically going to be colder than the water already in the tank. The reservoirs are above ground, so the water is going to be warmer than it would be in the pipeline below ground. So you bring colder water into the tank, which is containing water that's already been warmed by the sun or at least ambient temperatures. The cold water typically remains near the bottom of the tank, while the warmer water is a little more buoyant, floats up to the top, and can remain there for a longer period of time. So as you can see in the exhibit, you've got even just a couple degrees of difference, but you can have significantly lower chlorine residuals in these different layers created by even that thermal stratification. So ultimately what you have is a significantly declining water quality. You can see in the exhibit the chlorine residual examples where you are maintaining 1 part per million or 1 milligram per liter down at the bottom, and maybe it's less than 0.2 up at the top. The other problem you can have is a growth of nitrites within the reservoir. Again, what prevents nitrites from occurring is typically maintaining a constant solid chlorine residual. So if you don't have chlorine to prevent nitrites from growing, then you're going to have a nitrification problem in the reservoir as well. So These are significant problems in storage facilities, especially in the summer, and that thermal stratification can be even worse in the summer because the water is that much warmer. And from personal experience, we've seen significantly different or significantly greater water quality issues in storage facilities in the summer than we typically see in the winter. So it's something that has to be closely monitored and managed. So how do we manage that in a reservoir? Again, these reservoirs are important. We need to maintain water in the reservoir for a variety of the purposes we've already talked about, including emergency storage. And whenever you're talking about emergency storage, you potentially are talking about water for a longer period of time. In these operating reservoirs, even just the manner of which the water flows through the reservoir can have an impact on how old that water is and how difficult it might be to maintain those chlorine residuals. So there are different ways to deal with it. Some are reactionary or corrective maintenance activities. Other are more proactive or preventative maintenance. So one of the corrective maintenance activities when you start to have declining water quality or declining chlorine residuals is to accomplish some level of booster disinfection within the reservoir. And there's different ways to do that. One old school manual method of chlorination of a reservoir is simply to take bottled chlorine, and what you're looking at in this picture is pretty similar to the chlorine you would buy for a swimming pool. It's basically 12.5% sodium hypochlorite in gallon bottles. And what we would do is carry those bottles up the stairs to the top of the reservoir and dump the chlorine or the sodium hypochlorite in the hatch to add to the chlorine residual. Well, there's some serious issues with that approach. Sure, we can do the math and say how much chlorine do we need or how much sodium hypochlorite do we need to accomplish an objective, but it's a significant impact on labor to haul those bottles up those stairs, and we're literally talking about 50, 60, maybe even 70 gallons, so multiple trips carrying those things up the stairs. You're dumping it in a hatch. You're not really getting a great mix. You're getting a pretty concentrated amount of chlorine where it hits the water. It's not mixing real well, and we're basically adding chlorine directly, so it's essentially free chlorine, which can contribute to disinfection byproducts. So we're trying to accomplish the objective of resolving a declining chlorine residual, but there are issues and some downsides with that approach. Next evolution of the approach was a trailer-mounted pumping system where we would actually put the sodium hypochlorite in a vessel you can see on the back of this trailer, and then we had an injection pump. The nice thing about this is, A, we weren't hauling the stuff up the stairs, and we were able to connect that pump to a port on the inlet-outlet line of the reservoir. So we would lower the level and then start a fill cycle. So as we were pumping the chlorine into the pipe as the water was flowing in, we were getting a far better mix than we were when we were simply dumping the chlorine through the hatch at the top of a reservoir. So definitely an improvement, but still free chlorine, still not a perfect mix, and still subject to the creation of disinfection byproducts. What you see a lot more now is some more level of automatic booster disinfection with the use of chloramines to avoid the creation of disinfection byproducts. A lot of these systems actually use on-site generation of sodium hypochlorite, and this is a picture of one of the on-site generating facilities. What you see in the foreground, the very edge of a little container here, is essentially a brine tank. It's salt, and then you see a electrolytic cell in a panel here, which basically is electricity, and then it's water. The three components that make up sodium hypochlorite are salt, water, and electricity. So we would put salt in a tank, run water through it to create brine. That brine solution goes through the electrolytic cell, and that ultimately generates a relatively weak concentration of sodium hypochlorite. But for reservoir disinfection residual management, you don't need a high strength, and that the strength of the on-site generation, we were getting somewhere in the 0.6 to 0.8% sodium hypochlorite, so far less than the commercially available 5.25 or 12.5% solutions. But again, when you're just talking about trying to maintain a chlorine residual in a reservoir, that's sufficient. And so you're making it on site. You're not paying to haul it to the site. You're not paying for all that water that has to get hauled to the site, especially with the 5.25%. The idea is sound. It's all right there. There are some challenges. They do take a lot of maintenance. So we've kind of gone back and forth on whether or not the on-site generation is something. I've got some operators who really don't like it because of all the maintenance involved. And that maintenance then kind of erodes some of the cost benefits of making it ourselves. But the other thing you see in this picture, this is on the left, the tank is the sodium hypochlorite that's stored. On the right is an ammonia tank. So once again, we are using both chlorine and ammonia in order to generate chloramines, which is how we resolve the disinfection byproduct. So now we're pumping this solution into the reservoir, so it's kind of now as well as solving the disinfection byproduct issue. So again, a far better approach. You can also accomplish the same thing using bulk storage. This is a facility we just recently constructed. Again, I've got some operators who were not real thrilled with the on-site generators. It's debatable. There are those that swear by them and others that aren't as happy with them. So it depends on the needs and variables associated with individual agencies and individual facilities. In this particular case, this is a site that has both a 2 million gallon and a 3 million gallon reservoir, so it's a lot more chemical that we were going to need. So we chose to use bulk storage. At one point we were using the 5.25%, but we were going through it pretty fast, and the 5.25% was getting much more expensive, and so we actually switched to the 12.5% material. We use it fast enough that the degradation of the material is not an issue, and it's far cheaper on a pound for pound basis because you're hauling less water. So the storage tank you see on the right side of the facility is a 2,000 gallon sodium hypochlorite tank. The building portion to the left, there's an ammonia tank in that building, as well as the chemical injection pumps. So this is a relatively small bulk storage reservoir management system, or chlorine booster disinfection system for a reservoir. You also have seen this picture before. This is a much larger booster disinfection system at our big reservoir, where we have both the we have both the storage of sodium hypochlorite. These are both 5,000 gallon tanks, as well as a 1,500 gallon tank for ammonia. Once again, adding chloramines to the water coming out of the reservoir to boost the chlorine residual, just at a much larger scale. Adding the booster disinfection, and yes, I see the typo there. I will fix that at a future date. Is part of the issue, but in order to fully benefit from the addition of the chloramines to the reservoir, we really need to mix the water in the reservoir better. So there are mixing systems to provide circulation within the reservoir. So instead of having that thermal stratification or even the simple stratification associated with a common inlet-outlet pipe, these different types of systems provide a much better circulation of the water to get a really good mix, not just of the chemical that's being added, but just of the water age, so that you don't have stratification. You don't have older water in one part of the reservoir than another. You get a pretty constant water quality throughout the reservoir. In addition to maintaining water quality of the water itself, as you're adding the chloramines, these mixing systems help mix the chemical, the disinfectant, through the water much better. There's a variety of different types. There are jet mixers. They're all typically coming with some kind of pump system. Different types of manufacturers. We've got a couple different ones in our system that all basically accomplish the same thing. The whole goal is to provide some circulation, and those systems do a real good job of it. Then that kind of complete picture, then, when you have the chemical injection, you've got the mixing system, is what we would call a reservoir management system. And what you have in that case, not only do you have your chloramine injection, not only do you have your mixer, but you have a chlorine analyzer that's dosing the water based on what the actual residual is. So now we're able to set it up with a set point that says, okay, we want to maintain a 2 milligram per liter residual in this reservoir. The system will then continue to monitor the water that's in the reservoir to assess what the residual is, and to the extent that you need more disinfectant, more chloramines in order to achieve that disinfection residual, then it'll start adding more. So it's an automatic control system that looks at the residuals you've got, and then will increase or decrease the amount of chemical being added in order to maintain a more consistent residual in that reservoir. So it goes a long ways towards improving water quality in the entire distribution system, as you don't allow the degradation of the water quality in the reservoir. And again, it's something that can happen pretty significantly, especially in the summer when you get that thermal stratification. Just that water age that this does a good job of resolving, both on the disinfection residual maintenance as well as the circulation itself. Some other operations and maintenance concerns or practices that we need to be aware of. When you get into cold weather climates, they can be a pretty significant issue for elevated tanks, both on the exterior as you see in this picture, but really the water on the interior. And it's really bad for the reservoir if you allow freezing conditions of the water within the tank. Ice that might build up can damage the structure of the interior of the tank. So one of the ways that you avoid the buildup of ice or potential cold weather issues inside a elevated storage tank is simply by varying the water level, making sure that the water is coming in and out so it's not sitting still. As we've talked before, anytime water is moving, it's much less prone to freezing than water that is sitting still. So getting that water level moving up and down relatively constantly is one way to avoid some of those cold weather issues for especially elevated storage tanks. Coatings, especially for steel tanks, you can see a picture of a coating material there. This is actually an older coating material. You don't see much of this anymore. It was an old coal tar epoxy. You see more kind of paint type coatings these days, but they're really about corrosion protection in order to, especially on steel tanks, and as we've talked before, steel tanks can corrode just like a steel pipe would. It gets worse as the water's a little bit warmer. pH can impact it. The presence of total dissolved solids can increase corrosion. So a variety of just normal water quality issues within a reservoir can exacerbate some of those corrosion issues. So coatings is one of the ways, especially on steel tanks, both on the interior and the exterior, that will help to protect the steel structure of the reservoir. Typically the interior is going to be a bit harsher environment. You'll see estimates of the useful life of coatings. I've seen them in the 5 to 7 year range. In reality, we get much longer life of these coating systems than that. I am not, by any stretch of the imagination, budgeting to replace coatings in our reservoirs every 5 to 7 years. We're typically seeing 10 to 15 years, if not longer. And it's good because it can be very expensive. I mean, you're talking about several $100,000 to coat the interior of a reservoir, and there are all sorts of regulations you got to deal with, from maintaining compliance with NSF standards relative to the contact of a coating with potable water, as well as some of the AQMD standards. And that's a kind of a moving target. I've had a coating manufacturer representative show up in my office multiple times telling me, hey, this particular coating material, if you're interested in coating a reservoir, you got to do it soon because it's not going to be available after a certain date because it's getting regulated out of the market. So you got to kind of keep an eye on what is meeting current standards anytime you're looking at a material like that. In addition to the coatings, you can use cathodic protection on a reservoir, on a steel structure. Again, much like we've talked about with pipelines, that low voltage current will make the structure cathodic relative to sacrificial anodes that you're going to be using as well, and transfer the corrosion to the anodes as opposed to the structure of the reservoir. Of course, anytime you're using sacrificial anodes, as we've talked about before, you need to replace them as they wear, as they dissipate, as they're used up. They typically, in an environment like this, can probably, depending on the manufacturer, depending on the type, get you plus or minus somewhere around 10 years before they have to be replaced. So it's not like you're out there every few months replacing your anodes. But it's something to keep an eye on. One of the reasons some agencies might go to cathodic protection in addition to a coating which typically you're going to have a coating no matter what. Anytime you have a coating, if you've got any kind of pinhole or what they call a holiday, then that's where the corrosion is going to go off relatively quickly because it's not protected. So cathodic protection might be the backup to it. We are not doing that. We're relying primarily on our coatings. The cathodic protection can be a supplement to it, but if you have, depending on how you're operating it, and we actually had one reservoir where we had a cathodic protection system and a coating, and the operation of the cathodic protection system was actually damaging the coating. Now that's a unique case. I'm not suggesting by any means that it happens everywhere. There are successful applications where agencies use both, so it depends on the individual location, depends on the variables associated with an individual site. But overall, again, the important thing is we got to make sure that we're paying attention to protecting the steel and the structure of our reservoirs. They're huge investments. We got to make sure that they're well protected, much as we've talked about larger steel pipelines below ground. We've talked before about level in reservoirs, the instrumentation associated with measuring level, and you see this same picture of a level transducer we've seen before that's providing a signal to the local PLC and ultimately to our SCADA system so that we know what the level is in that reservoir at any given time. We also are evaluating oftentimes what the volume is in reservoirs based on that level. We've got tables that'll tell you, okay, every foot is a certain amount of volume. It's pretty simple math. That once, so you know the level, you can pretty easily equate it to the volume in the reservoir. Of course, we've touched on the fact that maintaining level control in a reservoir, and again, it's all about trying to avoid overflowing the reservoir, and we do that typically with altitude valves, and ultimately, as we've talked before, we manage the potential overflow of a reservoir with an overflow pipe. One of the other things to pay attention to in reservoirs is we can accumulate sediment on the floors. It is something that can be a water quality problem, especially if you are taking water down relatively low or draining the reservoir to a significant extent. This kind of thing can be cleaned up during maintenance activities. It's also something that literally can be vacuumed up by divers, which is something that we've successfully done occasionally, depending on the nature and magnitude of the problem. And then ultimately, as with any important facility, we need to pay close attention to it. We need to inspect it and to evaluate its ongoing condition and see problems before they become too big a deal. The inspections we'll talk about here come from recommendations from the American Water Works Association that have defined some different periods. The first one that they've talked about are what they call routine inspections, and these are typically going to be somewhere in the from a time frequency, daily or weekly, depending on agencies, depending on resources. And this is really a visual inspection from the ground. It does not require entering the reservoir. It doesn't even really, as it's defined, require getting on top of the reservoir. You're just taking a look at it from ground level, looking at the exterior, looking for any evidence that there's been any intrusion of the tank. Is there any vandalism, graffiti? Are we seeing example or any incidents of places where the coating might be failing? Are there any other structural issues? Is there anything about our site security that jumps out of this? So those are the types of things that you're going to look at on a regular basis. Now, again, this is just kind of defining a framework for inspections. I'm not going to suggest that everybody follows this to the letter, because I'm here to tell you we will be getting on top of our tanks and looking at it more thoroughly, much more frequently than what this would suggest. But the next version is periodic inspections that are theoretically quarterly. Now this is one where you are going to see things you can't see from the ground. You get on top of the tank, you're going to look at the roof hatch, you're going to look at the vents. Again, you're going to verify security, especially of your roof access, your hatches and your vents, to make sure nothing bad is going on with any kind of malicious access to the reservoir. So again, we, El Toro Water District, are going to do this more often than quarterly, but just understand the different levels of what these inspections would entail. And then a much bigger one is going to be a comprehensive inspection. This is now a inspection where we're going to get inside the reservoir. We're going to do some level of detailed evaluation of the interior of the reservoir, as well as continue to look at the exterior. Timing on these is not something that is clearly prescribed. I've heard it suggested that that you want to do this annually for elevated tanks or every 3 years for other tanks. I'm not going to say that those are hard and fast numbers. I'm here to tell you we do not do a well, I take that back. We do do an inspection of the interior of our reservoirs every 2 years, but we do it with divers as opposed to draining the tank and going into it. But we're looking at things, we're looking for things in these kind of inspections. Again, it's a much more detailed evaluation, especially of the interior. So we're looking at the coatings, we're assessing the reservoir, any kind of structural issues, we're looking for corrosion, and we're looking certainly for any evidence that anything might be wrong with the tank itself. If we talk about some types, especially of interior inspections, so how can we see the interior of a reservoir? The first is what we'll call a visual inspection. This is simply draining the reservoir, maybe 50%, and looking through the hatch and seeing what we can see. And this is typically something you might do between the more detailed, comprehensive inspections, so we don't forget about it in between and just look and see, all right, from the surface, is there anything I can see? The concept of a float down inspection is literally lowering the level again to a point where you have some access, and then putting a rubber raft in there and floating around and looking to see what you can see. And I'm a big fan of the dive inspections. We do these every 2 years on our tanks. We do it every year for our big reservoir. And the divers can get in there with they can do videotape, which we do on our big reservoir. They can take photographs, which we do on our tanks. Do damage estimates. There's a significant amount of underwater repairs that can be made. There are underwater epoxies. If you've got a coating failure, maybe there's one particular place where it looks like the coating is failing, there are underwater repair mechanisms to do that, which you can accomplish without taking the reservoir out of service. We talked before about the sediment removal that you can do with divers. So a whole lot of, and there's a lot of companies out there that do these dive inspections that it's an important way to ensure the integrity of the reservoir. And then ultimately the most aggressive is to literally drain the reservoir and to go inside. You'll see things like, you'll get a better look at things like the structure of the reservoir. This is actually the top portion of a steel tank. And that plate you see there is often called a dollar plate, and basically what it is a way to transfer the load from the individual rafters that you see coming on top of that plate to the center column, which is what you're seeing, a center column in one of these steel tanks that all the roof rafters land on to provide the structural support for the roof. One of the problems that we had not too long ago, and this was a vent on top of one of our reservoirs, and when we took it apart, we actually took it apart because we were going to do some coating work, and we were actually going to try and coat the top portion of that dollar plate. But as soon as we took the top off of this vent, one of the things we saw was the individual rafters that landed on it. And if you look closely, you can see that the structure of these beams is coming apart. I've never seen steel delaminate the way we saw on these beams. There were a lot of theories on what caused it, but all we knew is that we had a major structural issue with this tank and it could not be left alone. So what we ended up doing was what's called we had to take the reservoir out of service, and this is what's called a halo. So you can see that they were constructing just that, a kind of a circular beam mechanism around the that center column. Ultimately brought beams down to support that halo, and then as you can see, all of the rafter beams that previously came to the dollar plate were cut off, so we cut it back to a portion where that corrosion was gone, and then the more solid portion of the rafters remained tied to that halo, so all that load was then transferred to the center column by the beams connecting the column to the halo itself. So it worked. The project where we went in just to do a coating project ended up doubling in price when we had to do all the structural modifications. But that's the good thing about getting in and seeing the detail, is before something really bad happened, we found the deficiency and corrected it. So that is the specific approach to some of the different O&M practices relative to storage. We'll move from here into week 15, which will really be our last week of content. We'll talk about meters and services, and then following that it'll be time for the final exam. So we are in the home stretch. There's a light at the end of the tunnel. We'll hopefully navigate through this last couple weeks and then the final exam, which I'll put some more detail out about soon. But as we've talked before, it'll be comprehensive, covering pretty much everything we've done through the semester thus far.